data structures called hash maps and hash tables.
Okay, keep talking. Where does that, what do you?
So if you want to store an object, you want them all to be next to each other in memory, and an easy way to do that is to index them by what their hash value is, and that way you're like guaranteed that it's going to be unique or almost unique.
Almost unique. Yep. You might have two that overlap, but again, hopefully with the pre-image resistance, you are not going to have many cases of overlap. Absolutely. Okay, other ones. People were talking in their breakout rooms. What else do you come up with? Daniel, what else you got?
It's used in like PGP, which is an email encryption program. It's what my paper's on. And you just use it in like the signature scheme, which is kind of like what we're talking about, but like for verification, because you can like, they send the hash of the message and then you can compute the hash of the message you receive to check if they like are the same, because if not, you know that it was altered or something.
Yes, absolutely. Yep. And this kind of flows into another one. I'll go back to my slides in just a sec, but this kind of flows into another one related to computer security. So you can create a hash of a file at 2 different times. And if the hash changes, then you know that the file has been corrupted, right? That would be another possible way. I don't know if this actually gets used in practice or not. Again, I'm theoretically. Oh, yeah. Somebody's saying, yes, it does.
Yeah.
Yes, yes, it does. Okay, so then you know your file's been corrupted. That's another one. Elijah, yeah.
Yeah, along those same lines, I know anti-malware. So you hash you hash files that you know are like malware, like viruses, and then you can use that to scan for like malware on your computer.
Oh, okay. So you're looking for the hash instead of looking for the actual. Got it. Makes sense. Okay. Other ones that people came up with that you talked about. Other ones here. Okay, let's go back to my slides and we will see what I all have here. I think most of these we've talked about. So message integrity, create a hash of a message or a computer file at 2 different times. And then again, if the hashes are different, then the file's been changed or corrupted or whatever you want to say. So that's one. This is what Elijah was talking about, file identification. So instead of looking for an entire file, a computer might look for a hash instead. So you can index files by their hashes instead of by the whole function. Password authentication, this is what we talked about. Again, it was a very, very, very bad idea to store plain text passwords in a database. Very bad idea. And so you store hashes of the passwords instead. And we want to compare the hash of the passwords. Couple others. Message signatures. I don't know if we kind of talked about this. So messages, remember we've got these signature schemes, right? We have a message, we sign it. We said encryption is totally different from the signature scheme. So usually a message is long and it's going to take a while to sign it. We have power mods going on in the Elgamal scheme. We've got exponentiation and RSA signature schemes. And if your message is long, that's going to be a pain in the butt to sign. So what you can do is sign a hash of the message instead. And then you would send your message and the hash and the signature, and you would check the signature against the hash instead of checking it against the message. It adds a layer of complexity because now you've got 2 functions that you're working with. You've got the signature scheme function and you've got the hash function. So it does add a layer of complexity, but it also helps you out because now the signature function doesn't have to be quite as flexible. You know that the signature function is taking something input a fixed length. So it doesn't have to be quite as flexible if you are dealing with a hash function here. And then sometimes these are used to build encryption functions also. So sometimes it's difficult for your encryption function to take as input arbitrary lengths. And so hash functions help us out with, we're taking something of arbitrary length and getting it down to fixed length. So sometimes hash functions are just used to get us down to fixed length. That's where these sometimes come into play also. There are more. I'm quite sure there are more. I popped into a couple other breakout rooms. I'm sure you guys are talking about other ones as well, but the ones that probably on the first slide are the biggest ones where they get used. Okay, John, yes.
So I would like, sorry if this is too loud, I don't know.
So
if your encryption function can or deals better with like a fixed length or shorter than the actual message, so you hash it up? What if, I don't know, if you're sending something over a limited bandwidth channel and the output of your hash function is too long? Is there, like, if you truncate your hash output, is there any way you can determine, like, I don't know, half of it is half is secure if you use the first half? Does it work like that?
You have now said words that are practical, and we are getting out of my area of expertise. Maybe, possibly, I am not sure. I would have to do some looking on that. You're going to lose some of the security because you are only getting half of the hash function right, and that introduces the potential for more collisions, because you could have a collision, something that appears to be a collision that matches in the first half but not the second half. And so if you're only sending the first half of the hash, then you're going to get more collisions. So yes, you're going to sacrifice some security. How much, depending on whether speed is worth sacrificing that security, it's a balancing act. So yeah. Other ones, other questions before we talk about examples? Good questions. Other ones? Okay. Let's look at an example that is completely impractical, and then we're going to look at one that actually is a real example. So here is my hash function. M is an integer. That's going to be my input, and my integer can be of arbitrary length, so no problem here, all good. This satisfies the first half of the first requirement, arbitrary length. My parameter in this case is n, which is a large integer. And then the output of my hash function, I am going to take my input and mod it by n. So take my input and mod by n. That's the way that we are doing this hash function. This is a ridiculous hash function, by the way, but I want to get you a practical example of something you could potentially use that satisfies arbitrary length input and fixed length output, okay? So this is what we're doing. We're just taking our message and modding it by n. That's it. That's all we're doing. I'm going to put you back into breakout rooms, and I want to have you please discuss which properties are satisfied. So ease of computation, pre-image resistant, strongly collision-free, and weakly collision-free. I'm going to put you back in your same breakout rooms, I think. So which properties are satisfied with this? Breakout rooms. Okay, those should be open. You can go ahead and pop in. Just discuss which of those properties are satisfied, please. Go ahead.